All right, so first we have the original equation. The first thing that we're going to do is we're going to calculate the number of possible positive roots. We're going to do that by connecting the coefficients. Some people were trying to go too far, like they were doing too many loops, so just go from one coefficient to the next. So from here we went from a positive 2 to a positive 5, so there was no sign change. Positive 5 to negative 8 is a sign change. Negative to a negative is not. Negative to a positive is, and positive to a positive is not. So if we count up our yeses, that should tell us how many positive roots we have. We have 1, 2 yeses, but then don't forget you have to subtract 0, or subtract 2, which leaves us with 0. Now we're going to change it to the other equation that can get us the negatives. So we're wanting to find what would happen if we plugged in a negative x wherever we had an x. The shortcut that I gave you guys is wherever the exponents are odd, you change the number in front. Wherever the exponents are even, you keep them, and you keep the constant. So this is odd, so we're going to change the number in front. Even, we keep. Odd, we change. Even, keep the negative. Odd, change, and the constant we keep. So this is what our new equation is going to look like. And again, we're going to connect the coefficients. So negative to positive is a yes. Positive to positive, no. Positive to negative, yes. Negative to negative, no. And negative to positive, yes. So this should tell us how many negative real roots we're going to have. And it looks like we have 3 yeses, but you always have to subtract 2 to account for imaginary pairs. So you could also have just 1 negative. I'm going to use this information here to make a chart of what the nature of the roots could look like. So I know that I have to have a degree of 5. So every row has to add to 5. I could have positive numbers, negative, or imaginary for my roots. So I'm going to pair. What if I had 2 positives, and I'll pair that with 3 negatives, which would leave nothing for imaginary since I already have all 5. But instead of pairing 2 with 3, I could pair 2 with 1. So I could pair 2 positives with just 1 negative. That's 3 roots accounted for. I have 2 left for imaginary. If I continue this, instead of starting with 2 positives, what if I started with none and had 3 negatives? That's only 3. I need 2 more for imaginary to have that row total 5. And then I could also pair 0 with 1. That's only 1 root. I need 4 more. And again, we notice that the imaginary column is always even numbers because imaginary numbers always occur in pairs. So if I were Descartes, what would he suggest that I try first? Positive or negative?
Negative.
Yeah, because you're guaranteed a negative, but you might not get a positive for this. So he would suggest try a negative. So at this point, I would go to my calculator, and I'd probably graph this. Make sure that your calculator screen, always double check it to make sure it matches before you hit graph, just to be sure. And we're going to look at where it crosses through. Well, where might it cross through? That's what the rational root theorem is going to tell us. So we're going to make a list of our p's, which are all the things that go into 9, plus or minus 1, plus or minus 9, plus or minus 3. We're going to make a list of our q's, all the things that can go into the leading coefficient, which are plus or minus 1 and plus or minus 2. We're going to individually place all of our p's over all of our q's. So 1 over 1 is 1, 9 over 1 is 9, 3 over 1 is 3. Then we have to put them all over 2. So 1 over 2 is 1/2. 9 over 2, 9 halves, and 3 over 2, 3 halves. So we have 2, 4, 6, 8, 10, 12 roots. we should probably try a negative, and we're going to look in the calculator and see where it looks like it's crossing through. So when I put this in my calculator, it appears to me in this problem, it looks like this graph is going through at x equals -3. So I'm going to try that. -3 is one of the ones listed. We're going to use our coefficients of 2, 5, -8, -14, +6, +9. And we're hoping for a 0 in that remainder spot, which would mean it was a root. So we bring down the 2, multiply, write it up here, add, multiply, write it up here, add, multiply, write it up here, add, multiply, it gets written there, and we add, and then finally we multiply and add. So we have confirmed that -3 is in fact a root. We've also succeeded in taking this from an x to the 5th equation down to an x to the 4th equation. So if we wanted to see what it looked like, you don't have to write this every time. But if it helps you, you can. So that's what it would look like if you broke it down to an x to the 4th. But I have to keep going. My goal is x squared. So now I need to go back to the calculator screen and look for another value where it appears that it's crossing through, such as -1. So I'm going to use -1 and the new coefficients so that I can go down another level. So the new coefficients here were 2, -1, -5, 1, and 3. And again, I'm hoping for that 0 in this last spot. So I bring this down, I'm going to multiply and add, multiply and add, multiply and add, and we were successful in getting another root. And we went from an x to the 4th to an x to the 3rd equation. So we're going to break it down one more time. So we have to revisit the calculator yet again. And we're going to see that another spot where it looks like it's going through is at +1. So I'm going to use +1 and my new coefficients right here. 2, -3, -2, and 3. One more time, I'm hoping for that remainder of 0. Bring it down. Multiply, add, multiply, add, multiply, add. And again, I found another root. And I've broken it down from an x to the 3rd to an x to the 2nd equation. I'm hoping that this will factor, and we are lucky that this does factor. If not, we could have used the quadratic formula. It factors into 2x minus 3 and x plus 1. So if I set each factor equal to 0, I get x equals 3/2 and x equals -1. So when we're all done, we should have a total of 5 roots. Let's just make sure we have them all. So the roots that worked, this was one here at x equals -3. Here's another one at x equals -1. I'm going to hold off on listing that for a second. Here's another one at 1. We also have a root at 3/2. And then I said I was going to hold off on the -1 because we got -1 as a root right here, but didn't we also get -1 as another root right here? So what can be said about this root? It's got a special name. When it appears twice, it's a double root. So you have to note that. Because if someone's looking at this and they're like, well, that's an x to the 5th. You said it should have 5, but I'm only counting 1, 2, 3, 4. If you don't write this, you haven't told somebody what's happening. So when I look at this and you write this down, I see, oh, there's 1, 2, 3, 4, 5 roots. All accounted for, and we have our final answer. So then one last thing, if we looked at the nature of these roots and came back up to Descartes' Rule of Signs, it looks like we have 1, 2, 3 negatives, 2 positives, and we did have that right here. 2 positives, 3 negatives, no imaginaries. Descartes was accurate in his prediction. So that takes us start to finish through one of our longer problems.